Every time you take a breath, break a sweat, or stir a spoonful of sugar into your morning tea, you're watching a complex molecular interaction play out. These events rely on a specific interaction between two roles. First, there is the solute, the substance being broken down. Then there's the solvent, the substance doing the breaking down, which is usually present in a larger amount. People often confuse the word solvent with soluble, but they describe distinctly different things. If something is soluble, it has the chemical ability to be dissolved. The solvent is the environment that actually does the work. In a homogeneous mixture, solute particles fill microscopic gaps evenly. A drop from the top and bottom are chemically identical. But mix chalk dust, and particles refuse to break apart, suspending until gravity pulls them into clumps at the bottom. When matter blends perfectly, it creates a true solution, a state where the individual components are distributed with total uniformity. We normally think of these mixtures as liquids, but the physics apply equally to solids. When you expose different metals to extreme heat, their atomic structures loosen enough to blend. The result is an alloy, like brass or steel, a solid solution locked into place. The same is true for gases. The air filling your lungs right now is a gaseous solution. Because nitrogen makes up roughly 78% of the atmosphere, it acts as the primary solvent. Oxygen, carbon dioxide, and other trace gases act as the solutes dissolved within it. If the physical state of the matter doesn't restrict these mixtures from forming, it raises a mechanical question. Is there a hard limit to how much of a solute a single solvent can swallow? From a glass of tea to a forged steel ingot, every solvent eventually reaches a physical capacity where it can no longer break down more material. This threshold is called saturation. Think of a liquid solvent as a room with a specific number of empty chairs. In an unsaturated solution, there is still plenty of physical space available. The solvent can easily absorb and break down more solute particles without any issue. Keep adding solute, and eventually every microscopic gap is filled. The solvent hits its absolute maximum capacity. We call this a saturated state. Any new material you add simply falls to the floor, completely undissolved. Occasionally, under highly controlled conditions, a liquid can be forced into a supersaturated state. It temporarily holds more dissolved material than theoretically possible, right up until the slightest disturbance causes the extra mass to crystallize out of the liquid. The primary tool used to manipulate these spatial limits is thermal energy. Heating a liquid excites its molecules, forcing them to move faster and spread further apart. That extra space allows hot water to dissolve solids much faster and in much greater quantities than cold water. A solvent's capacity is never a fixed number. It is a dynamic threshold that expands and contracts depending on how much thermal energy is applied. Heat does not increase solubility for everything. When gases are dissolved in a liquid, raising the temperature has the exact opposite effect. As lake water warms up, it physically loses its ability to hold dissolved oxygen, which can suffocate the marine life relying on it. Pressure also manipulates these boundaries, a relationship defined by Henry's law. High pressure forces carbon dioxide molecules into the liquid of a soda. The moment you crack the can and release that pressure, the liquid's capacity drops instantly, and the gas violently escapes as fizz. Adding a solute can even rewrite how a liquid freezes. By spreading salt onto an icy winter highway, the dissolved salt particles physically get in the way, blocking the water molecules from locking into a solid ice grid. The water remains liquid at temperatures where it would normally be frozen solid. These environmental variables determine how a substance behaves in the wild, deciding whether fish can breathe in a warming pond or if a frozen highway can be cleared by a handful of mineral crystals. As a solvent packs in more and more solute, its concentration rises. Because you are adding more physical mass into the exact same volume of space, the overall density of the liquid increases. To understand why this matters, we have to separate mass from weight. Mass is the absolute amount of matter packed into an object. Weight is just the localized pull of gravity acting on that matter. Archimedes' principle relies on density, not weight. An object's ability to float isn't about how heavy it is. It depends entirely on whether its density is lower than the fluid it displaces. If the fluid is denser, it pushes back with an upward buoyant force greater than the object's downward push. The molecular density of a fluid determines the upward buoyant force acting on an object. This ratio is what ultimately decides what sinks and what floats in our oceans. We see this mechanic push to its absolute limit in the Dead Sea. It is an extreme, naturally occurring solution, containing over 30% dissolved salts, nearly 10 times the concentration of normal ocean water. That extreme concentration packs a massive amount of matter into the water. It becomes significantly denser than the human body. The resulting buoyant force is so strong that sinking becomes physically impossible, allowing people to bob on the surface like corks. But that mechanical benefit comes with a steep biological cost. The extreme concentration creates overwhelming osmotic pressure, aggressively pulling water out of any cells it touches. This turns the lake into a dead zone, incapable of supporting aquatic life. From the salt on our icy roads to the extreme buoyancy of the Dead Sea, mastering the invisible molecular mechanics of solutes and solvents is the key to manipulating and surviving the physical world around us.